Thanks. All right. I want to spend a little time today talking a bit more about the structure of the optimality conditions, of the first order optimality conditions. And I think one of the things that I've gotten a few questions about this, so I think it's important to sort of go through this in a little bit of detail and try to extract a little bit more structure from all of this. Okay, so here's what I'm talking about. We know that Hamiltonian, which is equal to L plus lambda transpose F. If you look at this, you'll actually see that the state dynamics x dot equals F of x and u can actually be written. If you look at this system, you can see that if I take the derivative of this with respect to lambda, I wind up getting F, right? So this is equal to h lambda, and then there's a transpose on here because of the way the orientation of the vectors aligns itself. And then lambda dot, which is defined as minus hx. So we've got a system of the form x dot equals h lambda transpose. There's a transpose here. Lambda dot is minus hx transpose. Now, there was confusion, at least a few people, so I'm sure other people have this issue too. When you solve these problems, these equations here for the costate are not decoupled from these equations here for the state. This is a coupled system of equations. Just think about it. I mean, if you look at this, if I take dh dx in this equation, what do I get? I get dl dx plus lambda transpose df dx. So this is equal to minus the partial of L with respect to x minus lambda transpose the partial of f with respect to x, and then the whole thing is transpose. So you've got this whole thing transpose, as these are all row vectors. And you can see here that what is lambda dot a function of? Well, lambda dot is a function, let's just call it g, if you want to call it that, is a function of x. It's got to be a function of x. There's x in here. It's a function of u, and it's also a function of lambda. It's a function of u because f is a function of u, right? And L may also be a function of u. If you look at x dot is equal to f of x and u. So now you look at this and you say, all right, well, this is not a function of the costate. But it is a function of the costate because if you substitute in the optimal control is by definition a function of the optimal state and the optimal costate, and possibly time, right? So x dot becomes a function of x, if you're putting a star everywhere just for explicitness, u star, which is equal to f of x star, and then because all this is true, it's f of x star, lambda star, and t. And then the same thing for lambda dot. If you say lambda dot star, you get it's a function of x star and then u star, but u star is a function of x star and lambda star. So you've got lambda star and t. So you see that you've got two systems here, one for the state and one for the costate, but they're both functions of the other variable. There's no decoupling that takes place here, all right? The costate is not a separate system from the state. These are interlinked problems, all right? You can't separate them. So rather than, I mean, this gets very abstract because you wind up with this with a system where you're just seeing like general functions here. So what I think might be a little useful, and it may seem a bit repetitive, but I'm going to do it because I think it's important to see structure. To me, the most important thing is not buried down in the algebra. It's to see the underlying structure of the problem, and it's to see that things actually are related to each other in a certain way. So let's just look at this example. It's a kind of modification of the LQ problem. It's not exactly the same problem as I put up before, but so let's go through it. It's the integral from 0 to tf of I'm just going to do this problem. I'm not going to put q and r and all that stuff. It's just x squared, 1/2 the integral from 0 to tf of x squared plus u squared dt. Tf is fixed in this problem. I'm going to say x dot is equal to x plus u, and x at 0 is equal to x0. And this time I'm actually going to put x at tf is equal to xf. Okay, it is a modification because in the finite horizon problem I did before, I actually had a Mayer cost which was in the problem. This doesn't have a Mayer cost. So what I want to do is I want to just go through this, and I want everyone to start seeing structure. All right. It is not, this example is not about, let's go solve this problem, okay? I know all of you are in the, I want to get an answer mode, all right? But you can't be in that mode when you're trying to understand characteristics of optimal control problems. It doesn't work very well. You need to take a step back and try to understand what exactly is going on. So let's do this, okay? Because I think it's important that all of you start to show me that you have some understanding of this material. So if I want to solve this problem, what is it that I need to do? Okay, so I need to write down Hamiltonian. Okay, so what's the Hamiltonian for this system? It's 1/2 x squared plus u squared plus what? Well, everything's a scalar here, so just lambda times x plus u. Okay? Now, if I look at this system, I've got what's the optimal control for this problem? How do I get an expression for the optimal control? What's that?
To find u that minimizes h.
I can't hear you.
We should find an optimal u that minimizes Hamiltonian.
Yeah, you want to find an optimal u that minimizes the Hamiltonian, but in this particular problem, this is the beginning of trying to identify structure, okay? What do you know about this problem? Well, tell me something about this Hamiltonian. Don't tell me something you can infer from the Hamiltonian. Tell me, when you look at this expression, what can you tell me about the Hamiltonian?
An explicit function of type.
Okay. It's not an explicit function of time, but I'm not that far deep. I'm not even that deep yet. What's true about this Hamiltonian? It's quadratic in x and u. What is it? So maybe I should ask you a question. What is it not? It's amazing, right? It's so hard to do this, right? It's because you guys want to calculate, right? And you don't want to think, right? You can train a computer to calculate. Computers don't think for you. The worst thing you can ever give your advisor or your boss is, well, the computer told me that. The computer doesn't tell you anything. You tell the computer, and it gives you back what you asked it to do. What you asked it to do may have been complete garbage. So you ask it garbage, it gives you back garbage, right? Computers do no thinking. They do what you ask them to do. You put the mouse over something and you double-click. You asked me to open this thing up because you double-clicked. I didn't do anything, right? I don't do any thought. I don't do anything. It's a computer. Computers can't think. So tell me something about this Hamiltonian. What is it not? It's not. We already said that. Okay, what else is it? It's hard, isn't it?
It's a scalar.
It's always a scalar. Hamiltonian is a scalar function. The reason you're not able to answer the question that I'm asking is because where I'm going with this is, how are you going to determine the optimal control? That was where I started, right? So what are you going to do? And why are you going to do it? Not just what are you going to do, but why are you going to do it? Yeah, I didn't put any bounds on the control. Control is unbounded.
The Hamiltonian is continuous everywhere, so we can just set the derivative to 0 with respect to u.
What am I going to do?
We can set the derivative with respect to u to 0. Since
Derivative of what with respect to u?
Of the Hamiltonian.
Okay, so we can set the derivative of the Hamiltonian. Why can we do this? Why can we do that?
It's continuous everywhere.
That has nothing to do with it.
It's quadratic in u.
No, it's not because it's quadratic in u.
The partial derivative will be a function function of u. We have a
The partial derivative will be a function of u, right? So if I take the derivative of h with respect to u in this problem, I get something that is itself a function of u. If what I got here was not a function of u, then dh du equals 0 gives me no information about the optimal control, right? So it's useless if I write down dh du if when I take the derivative I don't get anything that's a function of the control because I'm trying to determine a condition for the control, right? And if the control doesn't appear in dh du, when will the control not appear in dh du?
when it's linear.
When it's linear in the control, right? If the Hamiltonian's linear in the control, you're not going to get something that's going to be a function of u because take a derivative of a linear function, you get something that's not a function of that variable anymore, right? So clearly, the fact that this is not linear in u, which is what I was trying to get you to say, it's not linear in u, right? It will give me something that's a function of the control. So what is dh du? Go ahead. This is easy. This one's easy. What's dh du? It's u plus lambda. Right? And that has to equal 0, which tells me that the optimal control is equal to minus the optimal cosine. See that? Structure. The optimal control is a function of the costate. It is not, it has to be a function of the costate. If it's not a function of the costate, what you're saying is that it doesn't matter what I set the control to. I can set it to anything. So I'm going to go into a little more detail on this in just a few minutes, all right? So now I know that. So what does this tell me? So therefore, I know that the state equation, which is x plus u, if I'm on an optimal solution, it's equal to x star minus lambda star, right? I put the stars in here on purpose this time because I wanted you to see what's going on with regard to the optimal solution, right? So I know that. What's next? What else do I have to do? Am I done? Have I solved the problem? No. What else do I have to do?
The costate dynamics.
Costate dynamics. Okay. So what's that? Which is equal to what? Minus x what? Right? Is that a plus or a minus? Right? Because it's minus hx, right? So it's minus x minus lambda. So this is a scalar. So take this off. Right? So now it says that lambda, if I can actually put this in one line. Lambda dot star is minus hx star, which is this. So my system, x star dot lambda star dot, is equal to this. It's equal to 1 minus 1 minus 1 minus 1 times x lambda star. Right? Now, if you look at that, you should see something in here. You should be, and what you should see is that x, the differential equation for x, whatever it's going to be, when I solve this, I'm going to get an extremal solution, is not just a function of x. It's also a function of lambda, right? The differential equation for lambda is not just a function of lambda. It's also a function of x, right? So x dot star is a function of x star and lambda star. And lambda dot star is also a function of x star and lambda star. If I know that that's true, what is it that you could say it, you could put it as a positive statement or a negative statement. What can I or can I not do? I have two differential equations that are functions of each of the other variables. What do we call this thing? We have a name for this. They're coupled systems, right? They're not decoupled systems. So if you're trying to say that, oh, well, lambda has nothing to do with x, so I can just solve it and then plug it into the other equation, you can't do that because it's a function of the other variable. These need to be solved simultaneously. You cannot solve them sequentially. You can't say, well, one gets solved and then you substitute it into the other. There's a reason for this. It's because if you look at the if you remember when you do the variations on these problems, you get this variation in with respect to x, and you get the variation with respect to lambda. When you get the variation with respect to x, when you write down the augmented cost functional, what is inside the integral that multiplies the variation with respect to x? It's the costate equation that's actually sitting there, right? So what you've got is you essentially have this thing where the augmented cost functional, when you take a variation with respect to x, gives you this thing that multiplies in front of it is the costate equation. So you've got this differential equation which gives you the influence of the sensitivity of the cost with respect to the state at any point. If I vary the state, right, because when I take the variation in x, it means I'm taking the variation in the entire trajectory, right? It's the function of time. So when I do that variation, it says that if I perturb x, the influence on the cost of that perturbation shows up in the costate. So the costate is giving you a measure of how much the cost changes when you vary the state. So if you freeze time and you think about it at any instant of time, it's saying that the costate is the sensitivity of the cost with respect to the state. Let's suppose that there was no sensitivity of the cost with respect to the state. Meaning if I change the state, I don't change the cost at all. What would that tell me? Think about it. I have a cost. Every time I put in a trajectory, I output some cost, right? Because these are functionals, right? So I stick in a trajectory, I evaluate. If I stick in different trajectories and they all give me the same cost, what does it tell me? Yeah, it tells me that there's absolutely, it doesn't matter what I do to the control, right? I can do anything I want. I'm not going to change the cost, so why am I solving an optimal control problem? The reason that you solve an optimal control problem is because there is a sensitivity, right? That sensitivity shows up in this quantity called the costate. The costate is telling you that if whatever the sensitivity is in your problem to a change in the trajectory, that has to be felt through this adjoint variable or this costate variable, which is the dual variable to the state. So if these things weren't related to one another, then there would be nothing to do, right? If this was independent of this, I'd say, well, I solved the costate equation. It has nothing to do with the state equation. Then it's saying that I don't have an optimal control problem because I don't have anything to do, right? So clearly you have to have a reason to want to vary the cost or vary the state so that you can figure out which value of the state as a function of time minimizes that cost, right? Because otherwise it doesn't make any sense. And that comes out very clearly when you look at these equations, that these equations are not unrelated to each other. They're related to each other. Now, let's go into a separate issue, because this is an example of this, and I've done a little bit of it before, but I'm going to go into a little bit more detail on this particular problem right now because it's actually interesting, and I want to make this point very clear, because when we get into numerical methods and you start thinking about how you're going to solve problems on a computer, if you have no understanding of what it is you're getting yourself into before you start coding something up, you're going to be paralyzed when you figure out that things don't work exactly the way you would want them to. All right? So this is the differential equations, right? What else can I do here? Can I do anything else? I mean, I've applied the optimal control condition, right? I've applied the minimum principle. I've figured out the costate dynamics. What else do I need to know? There's what's that? Boundary conditions, right? So the boundary conditions are on the costate, right? But what do I know? What did I give you in this particular case? This is something that you have to understand if you're going to do this, on a more complicated problem. I gave you an initial value of the state, and I gave you a final value of the state. So what do you know about the costate? What's the initial value of the costate?
We don't know.
You don't know, right? What's the final value of the costate? You don't know that, right? So you know that this is true. You know that x dot, I'm going to take the stars off now because it just gets cumbersome to write the stars. 1 minus 1 minus 1 minus 1 times x and lambda, and I have the condition that x at 0 is equal to x0 and x at tf is equal to xf, and I said tf was fixed, right? So given the fact that that's the problem I have to solve, let's let's try to, can we, what can we do to try to solve this problem? Or at least make an attempt to try to solve this problem. Yeah, I'm saying, like, what kind of system is this? It's a linear dynamical system, right? And it's a constant coefficient linear dynamical system. So it's a time invariant linear dynamical system, right? So since it's time invariant, what do I know the solution is? Don't get fancy on me, all right? Do this with undergraduate methods because it's easier to see what's going on. You start getting fancy on yourself, you don't understand what's going on. So how do I solve a problem of this kind? I've done it once before. I'm trying to remind you because I know that whenever I do something, you guys don't remember it. I'm seeing that. It's becoming very clear to me that something I did 2 weeks ago, you won't remember it. So I'm going to reinforce it by doing it again. All right? So what's the solution to this problem? Oh, I'll make it easier for you. Well, I think it's going to be easier. I'm going to say let P equal x lambda. What I've got is I've got P dot equals A times P. What's the solution? Yeah, I knew you were going to do that. I told you not to make it complicated. This is a great example of you guys wanting to calculate rather than thinking. All right? What's the solution to this problem?
Transition matrix.
That's the same thing as the matrix exponential. It is the transition matrix. Eigenvalues and eigenvectors. That's what I want to see. What is the solution to this problem? P of t is equal to what? It's equal to, in this case, how many eigenvalues and eigenvectors are there? There are 2, right? So it's equal to C1 times V1 times e to the mu1t plus C2 times V2 e to the mu2 times t, right? I don't know what these constants are. These V1 and V2 are the eigenvectors. How do I get the eigenvectors? Oh, come on, you can't tell me you don't know how to do this. It's a two-dimensional problem, all right? I mean, this is an undergraduate problem. You should be able to do this, right? Come on. What do I need to do? I need the characteristic equation. Okay. All right. What is the characteristic equation? Notice I'm not using lambda for my eigenvalue, right? Because I got lambda as the costate. All right, so I'm using a different symbol for the eigenvalue, right? So shouldn't throw you for a loop. By the way, I do this to my undergraduate students. I'll change theta to phi, and they freak out. I thought it was always theta. It's like, well, why does it have to be theta? Theta is just a symbol, right? I call it whatever I want to call it, right? It's an eigenvalue. I called it mu, right? How do I get the eigenvalues and eigenvectors? Characteristic equation. What is that? What's that? No, s squared. Where'd you get s squared from?
I mean, yes, I mean this determinant of
Okay, all right. Determinant of what?
s minus 1.
There's no 1. You guys don't know how to remember how to get eigenvalues and eigenvectors. This is terrible. Come on. There you go. Si minus a. What does that have to equal? 0. Why is that true? I'm giving you a test on a question on a qualifying exam. Why is that true? See? What's that?
We are finding the roots.
But no. You're telling me what the result is. I want to know why this is true. Why is it that determinant is 0? By the way, I'm helping you out here. Okay, this has nothing to do with optimal control, but I'm helping you out because at some point, some of you are going to take a qualifying exam, and you're going to have to answer questions like this, right? Why is it that determinant is equal to 0? If S is an eigenvalue of that matrix A. Harder. It's because you guys are too busy calculating. Okay? You know that what's the definition of an eigenvalue?
It's because
I'm going to use V here. AB is equal to what? We're not using lambda. Lambda's the costate. No, we're not. Okay, we can use mu. Okay, S mu. It doesn't really matter. Okay. So tell me what I know from this.
AB minus mu V equals 0.
Which tells me what?
A minus mu V equals 0.
mu I.
Now what?
Either V has to be 0 or
Either V has to be 0 or what?
A minus mu I has to be 0.
What? A minus mu I has to be 0?
Yeah.
It does?
It is not invertible. The matrix A minus mu I is not invertible, it's singular.
Why?
In general, we won't equal to 0.
Okay. V is not, so assume V is not equal to 0. Then what has to be true?
It has to be rank deficient
It has to be rank deficient. Why does this matrix have to be rank deficient?
so that it will have at least one null space, or there will be some vector.
If this matrix is not rank deficient and this is not 0, what does that tell me? If this were not 0, V is not equal to 0, and this matrix is not rank deficient, which means it doesn't have a null space, right? That means there does not exist any vector, any non-zero vector, such that if I multiply this matrix by that vector, I get 0. Which is not possible, right? Because the only way this can be 0 is if something multiplied by this vector v is 0, where this vector v itself is not 0, which means the only way that can happen is if this thing here has a null space, which means it's rank deficient, right? So this has to be rank deficient, which means, so this says that A minus mu I must be rank deficient. Right? Which tells me what? If this is rank deficient, what does that tell me? That tells me that the determinant of this thing has to equal 0. Okay? I don't know how many of you actually take like rigorous linear algebra classes, but I highly recommend you do it. Because there are two things in this world, mathematically, that are really, really important if you're getting a PhD in engineering. One of them is linear algebra, and the second one is real analysis, which I know most of you don't want to take, which is painful to go through. But you can't not know this stuff well. You have to know this stuff well. It's a requirement of getting a PhD, because otherwise you're just going to go out into the world and you have no idea why you're doing anything. You have no clue. The fundamentals are not with you, right? That's the only thing you got. In your life, when everything else breaks down, all you have left are fundamentals. That's it. And if you don't have those fundamentals, you've got nothing. You're just fishing. You know, you're just taking a pole, casting it out into the ocean, and saying, I hope I come up with fish, right? Not a very good thing to do. Not if you're trying to do science and engineering, all right? That's not a good way to go. All right, so I know that has to be true, so which is the same thing. So what is the determinant of SI minus A? Well, what's SI minus A? I'll give you a hint. It's a 2x2 matrix. S minus 1. What else? 1. 1. Right. So the determinant of this thing has to equal 0. So what's the determinant of this thing? I get S minus 1 times S plus 1 minus 1. Right? Which gives me S squared minus 2 has to equal 0, which says S has to equal plus or minus square root of 2. Right? So what did I just learn? I learned something. If in this particular case the eigenvalues are real. What else did I learn? The system's not stable, right? But what else? But what's interesting about the instability, right? So I've got mu1 is equal to, it doesn't matter what order you do this in, minus the square root of 2. And mu2 is equal to plus the square root of 2. So tell me something more about this. Yeah, the eigenvalues are symmetric about the imaginary axis. How about that? Really interesting, huh? So if I plot real versus imaginary, I have an eigenvalue here and I have an eigenvalue there, right? Which means that whatever the eigenvalue is in the left half plane, there's an eigenvalue with the same magnitude in the right half plane, right? In fact, it's a really interesting thing about Hamiltonian systems in general is that every time you have an eigenvalue in one half of the plane, if you split it down the imaginary axis, you will get an eigenvalue in the other half of the plane. More importantly, if you have complex eigenvalues, this cannot admit a complex eigenvalue. The reason it can't admit a complex eigenvalue is because if it did, what would happen is there's another property of Hamiltonian systems, which is that if there's an eigenvalue in quadrant 1, then there has to be a corresponding symmetric eigenvalue in each of the other quadrants, right? If there were an eigenvalue in quadrant 1, in this case, that would mean there would have to be one in quadrants 2, 3, and 4, but there can't be 4 eigenvalues because this is a two-dimensional system, so therefore it can't be in the first quadrant. It's got to be on the real axis, which is why these eigenvalues are both real, right? You can actually prove that about a Hamiltonian matrix, because this kind of matrix that you get when you're all done with this, if you actually look at a more general system, what you have is, if you look at the second derivative, I'm going to do this just for a general system. If you see that x dot is equal to h lambda, and you say lambda dot is equal to minus hx, if you take the derivative of this thing, if you take this whole thing as the vector field, right, you call this thing g of x and lambda. If I take the partial of g with respect to p, where p is equal to x lambda, what do I get? If I take the derivative here, I get h lambda x, and then I get minus h xx, and then I get h lambda lambda, and I get minus h x lambda. This is what's called a Hamiltonian matrix. And a Hamiltonian matrix has the property that I just alluded to, which is that the eigenvalues have to be in each of the quadrants. If there's one in one quadrant, there has to be a corresponding symmetric eigenvalue about both the real and the imaginary axes. All right? Now we can go back to what we were talking about. So what's the solution to this problem? So the solution to this problem, P of t is equal to, well, actually, we didn't compute the eigenvectors, so let's look at the eigenvectors, okay? How do I get the eigenvectors? I got to plug these things in, and I got to solve for the eigenvectors. How do I do that? So say mu is equal to mu1. I've got mu1 I minus a is equal to what? Well, mu1 is equal to the square root of 2. Well, it doesn't matter. It's called this. You see, negative the square root of 2. Okay? So if I put in the negative the square root of 2, what do I get into that? I get minus the square root of 2 minus 1, 1, 1, and minus the square root of 2 plus 1. And this has to be times v11, v12 has to equal 0, 0, where v1 is the first eigenvector, right? So what do I get? Now, either one of these equations will work, right? I get minus the square root of 2 plus 1 times v11 plus v12 has to equal 0, right? I can take either one of these equations. So you can say let v12 equal 1. So what does v11 have to equal? Well, if I put 1 in here, right, I get 1 over the square root of 2 plus 1, right, which is equal to 1 over 1 plus the square root of 2. What about the second eigenvector? Second eigenvector, mu equals plus the square root of 2, gives me the square root of 2 minus 1, 1, 1, and the square root of 2 plus 1 times v21, v22 has to equal 0, 0. So this tells me that the square root of 2 minus 1 times v21 plus v22 has to equal 0. Let's see if I did this right. Yeah, I did this right. So if I set v22 equal to 1, then what's v21? Put it to the other side. I get 1 over 1 minus the square root of 2. So my eigenvectors are these, right? I set these to 1. And I get 1 over 1 plus the square root of 2 and 1 over 1 minus the square root of 2. You can simplify those if you want to. It doesn't really matter. Okay, now, if I look at the solution to this problem, the solution to this problem is going back to the general form that I have over there, is I've got P of t is going to equal C1 times V1 e to the minus square root of 2 times t plus C2 times V2 e to the square root of 2 times t. What do you notice about that? In both directions of time, right? You could see that if I move forward in time, then there's going to be a component, component of this solution that's growing, right? It's growing at a time scale of 1 over the square root of 2, right? If I look at backward in time, there's a component that's growing, right? Now, let's think about this in a slightly different way. There's a reason why I posed this problem the way I did, by the way. So if I go back to the original system, I have p dot, well, let's put it in terms of x lambda again. I've got x dot lambda dot is equal to, where's my matrix again? What I got? 1 minus 1 minus 1 minus 1 times x lambda. But I only gave you conditions on x, right? So now let's suppose I'm going to solve this problem numerically. Okay? And I'm going to do it with a shooting method. So with the shooting method, the way I have to do it, because I don't know anything about the costate, right? I don't know the initial costate. I don't know the final costate, right? So in order to do this, I have to integrate this system, but I have to integrate it iteratively, where I guess the initial costate, and then I have to determine whether or not the final costate, whether or not I've gotten the right solution. How am I going to do this, right? So what I know is, I know that x, we'll do this forward in time. I know that x at TF has to equal XF. So suppose we guess lambda at 0, and we call this lambda bar. It's a guess, right? Then what I can do is I can integrate this, right? I can say that x of t, or x dot, well, we can do it this way. X of t and lambda of t, right, are going to equal this transition matrix, which I'll just label it. It's e to the at. I'll put it in now because I know what all this stuff is. Times x0 and lambda bar, right? But if I don't get the right value of the costate, what am I going to get when I get to TF? I'm going to get the wrong value of XF, right? So I'm going to have to iterate. I'm going to have to pick a new value for this lambda bar and then integrate again and see if I get closer to the value at TF, to the value that I know it has to be, right? And I'm going to keep doing that until I pick lambda bar to be the value that this is over here. Now let's look at the error in this equation. There's no error in the initial state, right? So if I look at this, but there is an error in the initial costate. So if I look at this problem and I say, all right, well, I got to figure out what happens to an error. So let's say let E equal x minus x star and lambda minus lambda star, where x star and lambda star are the exact solution or the optimal solution. I know that x star of t and lambda star of t and lambda star of t have to equal e to the at times x0 lambda star, right? But a general solution, which has the wrong costate, is going to look like this. Right? Where this is some other costate. It's not the exact costate. What happens if I subtract these? If I subtract these, I get e of t, which is my error, is equal to what? It's equal to the difference between these, right? It's equal to e to the at times what? Well, 0, and I get lambda bar minus lambda star. Right, well, let's call this lambda 0 star. Okay? Now, if you look at that, you see that there's an error in here, right? Because there's an error in the initial co-state because I didn't get it right. If I make a mistake here, how big is my error going to be when I get to the end? It's going to be based on the eigenvalues of the matrix A, right? Because I know that e to the AT is equal to what? It's equal to V times e to the dt, where d is the diagonal matrix of eigenvalues, times V inverse, right? So if I put this in here, what I'm going to get is, I'm going to get this error, E, is going to equal V times e to the dt times V inverse times 0 lambda bar minus lambda 0 star. So because e to the dt is equal to e to the square root of 2, I put this in the right order, minus square root of 2 times t, 0, 0, e to the square root of 2 times t, I get this times v, and then times 0, lambda bar minus lambda 0 star. Right? This is what I get. Inverse. Right? Now, if you look at that, you can see that this error has to grow in forward time at the rate of this right here, right? Which is the same thing I had over there. I just wrote it a little bit differently. But the point is, let's suppose now that my final time, because my final time is fixed, let's suppose my final time is extremely large, right? I want to solve this on a geological time scale. I want to solve it for eons. What's going to happen? I made a mistake in the initial co-state, and I've got to integrate these dynamics all the way to the end, right? They've got to integrate to the next ice age, right? If I'm integrating to the next ice age, what's going to happen here? My computer's going to say, forget you, I'm going to blow up on you, and you're screwed, right? It's going to say, I don't care what you do, I'm not going there, right? Because if I go there, I'm going to overflow my machine, because it doesn't matter whether I've got a 32-bit machine or 64-bit machine or 128-bit machine or a gajillion-bit machine. Eventually, the largest number that the computer can hold is going to be too big for the computer, right? And it's going to wind up saying, I can't do it because you're asking me for something that I can't hold, right? So it doesn't matter what I do. Eventually, no matter how much processing power you have, no matter whether you have a sledgehammer or you have a quill pen, you're going to get screwed on this problem if TF is big enough, right? So no amount of you having all the machinery in the world is going to help you. So if you knew that in advance, you wouldn't do this, would you? Right? But in order to know this in advance, you have to understand something about the structure of optimally controlled systems, especially these Hamiltonian systems. When you're integrating them from one end to the other, you can't just blindly plug in and say, oh, well, you know what? I got these differential equations. I'm just going to integrate, right? That's great if you're a sophomore in college and somebody gives you an absolutely brain-dead simple problem that has absolutely nothing useful about it at all other than I want you to do this for homework. But if you're actually doing a problem where it matters that you have to get a solution and it's a more meaningful problem and it's being integrated over a long period of time, which many optimal control problems, the time interval over which you integrate can actually be long enough so that you actually get completely hosed in the process of doing the problem. There's nothing you can do. You might as well just turn on the fire hydrant and just accept it, right? So you don't want to do that. The point being that this is not a simple thing to do. The technique of simple shooting, which looks great on paper, right? This looks great. You just say, well, I guess this, I get here, I look how big my error is. It says, okay, I need to pick another value. I keep doing this over and over again. You can wind up with a problem where if TF is large enough, you could get this to a very, very high accuracy. You may actually have this to many decimal places correct, that initial co-state. But even so, you still made an error. And if that value of TF is large enough, that error is going to grow. And this is with no error in the dynamics at all. Notice that? This is perfect, right? Because I've got the eigenvalues, I've got the eigenvectors. I know everything in this. So this is without introducing any error in the numerical in integration. You're not doing numerical integration. I'm doing analytic integration, right? So even with analytic integration, you could wind up being completely screwed. You could wind up in a situation where you wind up doing this, and you're like, I'm not making any error in my actual numerical calculations, to the precision that the computer can actually hold. But even so, I'm still going to overflow the machine. So the overflow of the machine doesn't have to do with the error in the numerical integration. Now, if you actually add that and you say, well, I'm not going to do this analytically, I'm going to actually use some kind of numerical integrator, whether that be like, an Euler method. Euler methods are terrible because they're only good to, first order. But I use a 4th order Runge-Kutta. I can use a 12th order Runge-Kutta. I can use a 500th order Runge-Kutta. It doesn't matter what I use. I'm going to introduce some discretization error due to the fact that I'm actually using a numerical integration scheme. That's just going to make this problem worse, right? So even in the case where you have perfect information, you wind up with an overflow. If you don't have perfect information, you wind up getting to that overflow even faster because you're introducing a second error, which is due to the numerical integration scheme. So this whole thing breaks down, and this is a really simple problem. This is an absolutely simple problem. I mean, if you just take your favorite calculator and just take e to the square root of 2 times t, and just plug in values of t, and eventually you'll find out your calculator is going to say overflow, right? I mean, if you take your calculator on your iPhone or something like that, right? It's pretty good. The scientific calculator on the iPhone is actually pretty good. And even then, if you make t large enough, you're going to wind up overflowing the calculator, right? And you say, well, that's a really simple function, e to the square root of 2 times t. I can't really think of something much simpler than that. It's polynomial, maybe simpler than that. But as far as like analytic expressions go, it's a pretty simple expression, right? But you're still completely like at a loss as to what to do because what you're doing is inherent in the dynamics of the system. It doesn't have anything to do with your particular iteration scheme. It has to do with the fact that the dynamics are actually unstable of this Hamiltonian system. And it doesn't matter whether you go the other way, because you wind up with the exact same problem if you go the other way, right? If I go backward, I wind up with the other eigenvalue giving me trouble, right? So if I'm integrating from tf back to t0, the square root of 2 times t now decreases in time, but the e to the minus square root of 2 times t explodes in time, right? Because I'm going backwards. So either way, I wind up with a problem, right? So the point of this lecture was for you to understand a little bit more about some of the structure of some of these problems on a simple example so you can actually see what's going on so that you don't just naively start putting things on a computer and just get yourself to the point where you're like, I have no idea what's going on, because it's really important to identify some of these things before you start chugging away with the numerics, okay? That's a good question. See, so now this should actually, that's a great question. So you should feel at this point like, wow, you know what? There's got to be another way to do this, right? Because this is not going to work on a general problem. So the next topic, or as we move through this class, where are we now? We're like not quite at the middle of February, so we're like 5 or 6 weeks into this class. Yeah, so we're just at the point where I'm going to start introducing you to numerical methods for optimal control, and we're going to start transitioning into that maybe Friday, most likely probably Monday, because I want to do one more thing on Friday. So next week we'll start talking about it. And you'll start to see that in a practical sense, this is what I call, there's the theoretical side of optimal control and there's the practical side to optimal control. And the reality is there are two ways to solve problems in this world, okay? This is not to like point fingers at anybody, so I don't want to say this the wrong way, which is that I want to solve problem X, but I can't solve problem X. So I'm just going to keep dumbing it down until I make it problem Y, which really has no resemblance to problem X whatsoever, but that's the problem I can solve. So I'm going to solve that, and then I'm going to make some really huge extrapolation that by solving problem Y, I've actually done something that's relevant to problem X, which is not the way that you want to do things in optimal control. It's like, I want to solve problem X, and I need a method that actually solves problem X, because I'm not interested in solving problem Y. Because from an academic standpoint, you wind up, well, I'll just solve the problem I can actually solve. And then you make some rationalization as to why that's a good thing to do, and then you write some journal paper on it, and nobody cares because it's not useful, right? If you're actually interested in solving a real problem, you have to focus on developing a method that allows you to be able to solve that particular problem. What I'm going to introduce you to with the numerical methods we're going to talk about in this class is geared towards being able to help you solve problems that actually arise in real situations, and you can actually apply them in practice. Okay, so this is kind of the practical side of optimal control. There's still a lot of math in it, but it's practical in the sense that you're no longer, working with continuous systems and all mathematical theory that we've been working with for the last several weeks. You have to sort of change your mode of operation. Okay? So we'll start talking about that next week. And then Friday I'm going to do one other thing. Okay?